We are moving on to theorem 3.7. The statement says that we are given with a open connected set G and a function from that set to C called f, which is analytic. Then we have to prove three equivalent statements. The first statement is that f is identically equal to 0. The second one is that there is a point A in G such that the nth derivative of f at A is equal to 0 for each n greater than or equal to 0. The third statement is set of all said in G such that f of z is equal to 0 has a limit point in G. So whenever we are assuming f is identically equal to 0, you get B and C to be obvious statements. And now we are going to prove C implies B. So we are assuming this, that the set of all elements in G such that f of z is equal to 0 has a limit point in G. We are assuming that, and we are going to prove B. Suppose A belongs to G and A is a limit point of the set here. We are notating it with a name Z. Z is equal to set of all Z belongs to G such that f of z is equal to 0. So A be a limit point. And also let capital R strictly greater than 0 be such that B A of R is completely contained inside G. That is possible because G is an open set. So whenever A belongs to G, you can find an open disk centered at that point A with a particular radius inside G. So that is a property used there. Now as A is a limit point of Z and F being analytic, it is continuous. We can say that A is equal to limit n tends to infinity Zn, because it is a limit point, right? So these Zn's are coming from the set Z we are talking about. Okay. So 0 is equal to limit n tends to infinity f of Zn. Why? Because Zn's are coming from this Z. So f of Zn will be 0. So 0 is equal to limit n tends to infinity f of Zn. That is equal to f of limit n tends to infinity Zn, because f is continuous. We can do that. Okay, that is equal to limit n tends to infinity Zn. What is it? That will be A. So that is equal to f of A. So what you got is 0 is equal to f of A. That means A belongs to this set, that is A belongs to Z. So that is an observation we got. A was a limit point of Z. Now you got that A belongs to Z. Suppose there exists an integer n greater than or equal to 1 such that f of A is equal to f dash of A is equal to etc. equal to f n minus 1 of A is equal to 0, and when it comes to the nth derivative of f at A, that is not equal to 0. So we are taking a negation of this. That means here this means that there exists a point A is that for every n greater than or equal to 0, the nth derivatives of f is equal to 0 for every n, right? So we are telling that up till n minus 1 this is 0, but at n, when we are talking about the derivative, the nth derivative of f at A is not equal to 0. So we are taking a negation of that statement, and then we'll reach a contradiction. Now, as f is analytic, it definitely has a power series representation about A. So f of z is equal to summation k is equal to n to infinity ak z minus a the whole raised to k, where modulus of z minus a is strictly less than r. Okay, define g of z is equal to summation k is equal to n to infinity ak z minus a the whole raised to k minus n. Fine. So that is when we expand, we know this is equal to, substitute for k, you get an plus, substitute for n plus 1, you get an plus 1 z minus a plus an plus 2 z minus a the whole square plus etc. Okay. By the definition of g of z, we know that g of z is analytic in the open disk BAR, And also by observation we can understand that f of z is equal to z minus a the whole raised to n into g of z by the definition of g of z. Okay. And also we know if a is substituted here, g of a, the rest of the terms will be 0 and what you are left with is an. So g of a is equal to an, but an we know it is the end, it is a coefficient of the term z minus a the whole raised to n in f of z, which is a power series. So by the earlier theorems which we did on power series, we know an is equal to the nth derivative of f at a divided by n factorial. And also we have assumed that this nth derivative of f at a is not equal to 0 here. So we can say that this an is not equal to 0. Okay. Now since G is analytic, obviously it is continuous. In BA of R, BAR, by the property of continuity, we can say that we can find an R which is happening inside 0 and capital R such that G of Z is not equal to 0 for modulus of Z minus A strictly less than R. Why? Because here G of A is not equal to 0. So we can find some points around that A. That means in the open disk modulus of Z minus A is strictly less than R, where G of Z is not equal to 0 by the continuity. But we have taken A to be the limit point of Z. Okay. So by the property of limits, we can say that there exists a point B with f of B is equal to 0 and 0 strictly less than modulus of b minus a strictly less than r. So this will imply that we are taking f of b here. See here you are taking f of b, that means f of b is equal to b minus a the whole raised to n into g of b. Okay. Uh, and we know that f of b is equal to 0. We are saying that there exists a point b such that f of b is equal to 0. So we know that f of b is equal to 0, that is equal to b minus a the whole raised to n into g of b, and b and a are distinct, so that means g of b is equal to 0, which is a contradiction. Why? Yes, to the fact that g of when g of b is equal to 0, you get a contradiction out there, right? So here no such integer n can be taken like that, where this fn of a is not equal to 0, and that leads to our theorem. And now we are moving on to the part b implies a. When we are talking about g of b is equal to 0, there the contradicting fact will be that g is 0 free inside b a of r. That is a assumption which we had inside here. Here we had said that we can find r such that g of z is not equal to 0 for modulus of z minus a is strictly less than r. That is the contradiction which we get here, because here this b is coming from modulus of z minus a, modulus of z minus a is strictly less than r. See, a point b. So that is a contradiction that you get there, to clarify if there is a doubt. So now we are moving on to b implies a. So what we are going to assume is B, we know that statement is there is a point A in G such that Fn of A is equal to 0 for n greater than or equal to 0. So we have to prove F is identically equal to 0. For that, let A is the set of all sets such that Fn of Z is equal to 0 for all n greater than or equal to 0. So we are assuming B, that means there is a point having such a property. That means this set we defined, which is A, is not equal to 5. Okay. So what is our idea? We will show that A is both open and closed in G. Okay. That is our A. We have to show both A is both open and closed in G. So suppose if we show that, how can you move to the proof? So if we prove so, by the connectedness of G, we have to say that every open and closed subset of G will be either phi or G. So here A is not equal to phi, which is already said. That means A should be G. So when A is equal to G, our conclusion is done. That becomes F is identically equal to 0, because every nth derivative is 0. That will mean for every point inside. So that means F is identically equal to 0. That's how we arrive there. Okay, so first we'll prove that A is closed. For that, uh, let Z belongs to A minus. A minus simply means A closure intersection G. That means set of all limit points inside this set. Okay, suppose set K be a sequence in A such that the limit of set K as K tends to infinity is Z. And it is clear that all the nth derivative of F is continuous. Okay. So we can say that Fn of Z is equal to limit n tends to infinity Fn of set K, because of the continuity. And these Fn's, the set we chose is coming from A, A bar intersection G. So, and also this, where are these set k's coming from? Set k's are particularly coming from A. So Fn of set K will be 0. So you get Fn of Z is equal to 0. So definitely this set is happening to be inside A. That means A is closed. So we took a limit point and we said that that limit point is inside that set. That means the set is closed. Now to show that A is open, let A belongs to A. Let capital R strictly greater than 0 be such that BA of R is completely inside G. We can define such an R because G is an open set. Now, since the function is analytic, it has a power series representation like this. For modulus of z minus a strictly less than R, and an is happening to be equal to 1 by n factorial into fn of a, and this fn of a will be 0 because this small a is coming from capital A. So this an is equal to 0 for each n greater than or equal to 0. That means the function is equal to 0 for every set in dA of R, and that will mean that the Z is belonging to A, which means that BA of A, BAR is completely inside A. That means when we take when we take a point small a in capital A, we can find an open disk centered at that point with a particular radius, and that is completely contained in the set A. That means A is open. So that leads us to the conclusion of the proof. Corollary 3.8 says that if f and g are analytic on a region G, then f identically equal to G if and only if set belongs to G such that f of z is equal to G of z has a limit point in G. You just have to think about f minus g. Take the function f minus g identically equal to 0, and the rest of the theorem falls into the proof from the earlier theorem. Now let's move on to corollary 3.9, which says that if f is analytic on an open connected set G and f is not identically equal to 0, then for each a in G with f of a is equal to 0, there is an integer n greater than or equal to 1 and an analytic function g from capital G to C such that g of a not equal to 0 and f of z is equal to z minus a the whole raised to n into g of z for all z in G, which means that every 0 of f has finite multiplicity. So to prove that, we basically know from the statement that f is not identically equal to 0. So we just had proved the theorem 3.7, which says when f is identically equal to 0. So we are taking the negation of that. That means you have negation of this statement. Okay, so you are taking the negation of the second statement there in this corollary, and that means there exists an n belongs to n such that fk of a is equal to 0 till that n. Okay, so that is the largest n such that it is equal to 0. Okay, now define g of z is equal to f of z divided by z minus a the whole raised to minus n. Okay, and for z not equal to a, and g of a at a we are defining it as fn of a divided by n factorial. Definitely the g is analytic in the set g minus set a. Okay, and we have to show that it is analytic at set is equal to a. For that, write the power series of f, the analytic function, which is summation k is equal to n to infinity a k set minus a whole raised to n. Okay, so then we have g of z is equal to summation k is equal to n to infinity ak into z minus a the whole raised to k minus n for z not equal to k, but an is equal to fn of a divided by n factorial. So this definitely, by the definition of g, we know that this definitely will be continuous at z is equal to a, and of course f of z is equal to z minus a the whole raised to n into g of z. So G being written as such a series, it will be analytic. So this proof is almost like an outline as we had seen in the theorem 3.7. You can rigorously write it out and prove it. Prove it. That is what you have to do there for corollary 3.9, and corollary 3.10 gives us the assertion that if we have an analytic function which is non-constant and f of a is equal to 0 at a point in the domain, then there exists an r strictly greater than 0 such that f of z is not equal to 0 for all points inside the open disk set minus modulus of z minus a is strictly less than r. That means all the zeros of f are isolated. That is another corollary which is inferred from the theorem 3.7. And now we move on to the important part of this section, which is maximum modulus theorem. which says that if G is a region and f from G to C is an analytic function such that there is a point A in G with modulus of f of A is greater than or equal to modulus of f of Z for all Z in G, then f is constant. So basically, we have to prove that f is constant with the hypothesis given. So for that, let B bar of AR is contained in G, which is the closed disk centered at A and R radius. Okay, and gamma of T is equal to A plus R e raised to IT, where T is varying from 0 to 2 pi. It simply means it is a circle centered at A and radius R. And by Cauchy's integral formula, which we had seen earlier, we know that f of a is equal to 1 by 2 pi I integral over gamma f of w divided by w minus a dw, that is equal to 1 by 2 pi I, the line integral definition. Integral 0 to 2 pi f of gamma of t divided by gamma of t minus a into gamma dash of t dt. That is equal to 1 by 2 pi I integral from 0 to 2 pi f of, instead of gamma of t, you can have a plus r e raised to it divided by r e raised to it plus a minus a. So you get denominator to be this. And gamma dash of t is nothing but I r e raised to it dt. So that is equal to, when you simplify, you get 1 by 2 pi integral from 0 to 2 pi f of a plus r e raised to it dt. Now we are assuming the hypothesis modulus of f of a is greater than or equal to f of z for every z in G. So take the modulus of f of a. So when you take the modulus of f of a, you get less than or equal to, but the property of integral and modulus, that is equal less than or equal to 1 by 2 pi I integral from 0 to 2 pi modulus of f of a plus r e raised to it dt, and you know that for every set that will be less than or equal to modulus of f of a. So this can be written less than or equal to modulus of f of a. That is what we have written here. So you get that is less than or equal to 1 by 2 pi integral from 0 to 2 pi modulus of f of a dt, that is equal to 1 by 2 pi modulus of f of a into, when you integrate, you get that is equal to 2 pi minus rho. So you get, you can just cancel out this 2 pi, you get modulus of f of a. So modulus of f of a here, modulus of f of a here, so everything in between will be equal to that, right? So you get from that, you can equate both of them sitting here. Okay, so you can take this 2 pi to this side, multiply and rearrange. Both of them are equal. What you get is this modulus of f of a, and the term sitting here are equal. That means you can just rearrange, and that is equal to 0. 0 is equal to 2 pi into modulus of f of a minus the integral sitting here. Okay, and that can be rearranged as that is equal to integral from 0 to 2 pi modulus of f of a minus modulus of f of a plus r e raised to it dt. We have assumed this, right? So the integrand above, uh, this one, the term stick here, that will be a non-negative quantity, and we are integrating it, and we are saying that when we integrate, you get it to be 0. That means the integrand has to be 0. We have no other choice. So that means modulus of f of a is equal to modulus of f of a plus r e raised to it for every t belongs to closed interval 0 to pi, and we have chosen r, small r, to be arbitrary. So this open disk is an arbitrary disk, and it is mapped to something of the modulus of f of a. So f maps b a r to the set of all sets such that modulus of z is equal to modulus of f of a. So we get that you can just verify how you get f to be constant there. So you can check out exercise 3.17 to work out there to get how this function is becoming a constant there. And that is how we end the proof of maximum modulus theorem here. Thank you for watching out. See you in the next lecture.